Hello teachers, welcome back to part 2 of section 6-1 where we're defining rational numbers. We are reducing fractions to what we call lowest terms and are completely simplified. And right now I want to start with the slide that I left off with in part 1, which is ordering rational numbers. And so when you have a denominator that matches, it's very easy to order rational numbers. The numerator that's larger makes the larger fraction. But when you don't have common denominators, it's not so easy. One method is you could build common denominators and then compare. Another method is to use equality of fractions like we talked about just a minute ago. So you can multiply numerator times denominator. Notice that the greater value here, the fraction that's larger, starts with that numerator times denominator. And then that's greater than this way. Notice it says AD, the pink one, is greater than BC, the green one. Now, in the last video, I made up an example, just made up one randomly on the spot to show you how that works. But they give us an example over here. So what I want to do is revisit this idea and compare. Now, we have 4/5. We don't know, greater than or less than right here, 11/12. Now, we can look at the picture and tell, but I want to see if we can tell from just doing this problem. So let's cross this way. 4 times 12, we know is 48. Again, we don't know what sign to put here yet. 11 times 5 is 55. Now, turns out 55 is greater. Notice when we started, you do greater than with the one you started with, right? 11 times 5 is 55. Since 55 is greater, that means I put a greater than sign here. Now, when I read this, it's not a greater than sign, it's actually a less than sign. 4/5 is less than 11/12, but I wanted the mouth open towards the 11/12. Now, you can look at the picture and tell that 11/12 is larger than 4/5 because we made our whole exactly the same size, right? Okay, I hope that better explains what I left off with in the last problem. Okay, let's keep going. Denseness of rational numbers. This is very interesting. It says, given any two rational numbers, A over B and C over B, there's another rational number between these two numbers. Always. Even if these numerators are right next to each other. So if I give you, say 3/7 compared to 4/7, there's still a rational number that fits between 3/7 and 4/7. Always. You can always find another rational number between two numbers, and that's why they call it the denseness of rational numbers, because there's always one in between. So I've got an example where we get to do that. It says find two fractions between 7/18 and 1/2. But now, if I go back, you'll notice that with the denseness, these have common denominators. But our problem that we have going on now, these do not have common denominators. So the place to start would be to write these with a common denominator. So I can multiply 1/2 by 9/9, right? This is the fundamental theorem of fractions, that you can multiply both the numerator and denominator by the same value. And we can compare 7/18 now to 9/18. Now, is there a number between there? Yes, right? 8/18 fits between those two fractions. But notice it said find two fractions between there. So one thing we could do is make the denominators even higher. Okay, so remember in pink, these are our endpoints. I've already found one fraction, 8/18, that fits in between there. But let's multiply these by 2. So 2/2 here. This is going to make our denominator larger. So this is going to be 14/36 versus 18/36. Hey, if I multiplied the one in green here by 2/2, this would give me 16/36. That's already an in between. What else could we use? How about 17? over 36, and we've done it. We found two fractions in between. If you ever have to find values in between and you don't have an integer that you can use in that numerator or a whole number that you can use, just make the denominator even larger and you can always find one in between. The typed up version of that, notice they did what we did. They found a common denominator of 18, and they found 8 over 18 fifths, which is 4/9. I never did reduce that, but that is 4/9. And they upped it to 36 just like we did. I'm scanning through very quickly, and I think it keeps going to the next page. 7 over 18, which was our endpoint, was 14 over 36. Okay, and 18 over 36, that's the other side. That's 1/2 is equal to 18 over 36. So it's easy to find fractions in between. 15 over 36, 16 over 36, 17 over 36, all of those fit between. Okay. All right, now more to this. Let A over B and C over D be any rational numbers with positive denominators, where A over B is equal to C over D. Then we have a really interesting theorem that, look, A over B is the one on the left. Okay, so this here, C over D is the one on the right. If you would like to find one in the middle, a cute trick is that you could add C to A and D to B. Isn't that interesting? We could have done that for the last problem. Think about that. Use that in the homework if you need to. All right, I've got one more example for you, and then we can wrap this up. And this is very similar to a problem that showed up in the homework. I'm sure you're capable of doing it, but just in case you struggle with it, I wanted you to see it. So for each of the following, choose the expression that equals or describes the best given fraction. Complete A through C. Now, we're not going to choose the following. This is not multiple choice. I just want to knock this out and get it done. When you look at the first problem, we have 35 plus A divided by 5A. Now, you want to simplify this. We have done a problem identical to this in part 1 of our video here. I cannot divide 5 into 35. I cannot divide A into A. I need to factor, using the distributive property, a greatest common factor, but I don't have one. So this does not simplify. Okay, so the first one does not simplify. Let's move on to the next one. I have 2 to the 10th plus 2 to the 9th. Please don't tell me that's 2 to the 19th. We cannot add those together like that. And divided by 2 to the 8th plus 2 to the 11th. But they do have common factors. If I use the distributive property backwards, notice 2 to the 10th is bigger than 2 to the 9th. I can pull out the smallest of the two. So 2 to the 9th comes out. 2 to the 9th times 2 to the 1st really gives me 2 to the 10th. And we know 2 to the 1st is 2. Plus, if I pull this entire 2 to the 9th out, I need a 1 to hold that position. I'm going to do a similar thing in the denominator. Okay. Now, can I pull out a 2 to the 9th? I can't. I can pull out a 2 to the 8th, though. That's the smaller of the two. So 2 to the 8th comes out. That's going to leave me with 1 plus. Now, if I pull out 8 of these, that's 2 to the 3rd still left inside. Now, why did I do that? Because this is multiplication right here, and I can cancel this 2 to the 8th with 2 to the 8th here, and that's going to leave me with 1 left over. Okay, so 2 to the 1st remains there. Now, in the parentheses here, 2 plus 1 is 3, and in the denominator here, 2 to the 3rd is 8, plus 1 is 9. I could even take this further and cancel this 3 and this 9, and that leaves a 3. So this finally reduces to 2/3. Now, if you didn't think about it exactly like that, that's okay. That's a pretty efficient way to do it that I just did. But there are other approaches, but I think this is probably the easiest one for sure. Definitely don't calculate 2 to the 10th and add 2 to the 9th, and same with the denominator, and then try to simplify it because the numbers are enormous. You don't want to do that. Now, I want you to pause it and think about the next problem exactly the same way as you did B. See if we can knock this out, and this is the last problem we need to do in this video. All right, did you get it done? Okay, so look at, you've got 2 to the 113 power and 2 to the 111 power. Now, the smallest of those is the 2 to the 111. I'm going to pull that out. Now, if I pull out 2 to the 111th power, which is huge, by the way, so don't try to type that in your calculator and do this just with whole numbers. It'd be awful. Okay, 2 to the 111 comes out. Now, I've pulled all but 2 of those out, so that's 2 to the 2nd is still in there. Remember, when you multiply bases, the rule is you add those exponents together. Now, this, I've pulled all of this 211 out, so I just need a 1 there to hold that spot. Now, let's do a similar thing in the denominator. Look, when I compare these two, even though it's subtraction, that's just going to leave a subtraction in our, when we do the distributive property. So this 2 to the 111 comes out. All right. If I pull 111 out here, right, that's still going to be 2 to the 2nd that remains, and that's going to be minus 1. Now, again, you know what's going to happen. A lot of students are going to cancel this 2 to the 113 over this 2 to the 113, and this 2 to the 111 over this 2 to the 111, and all you have left is a plus over a minus, which doesn't make any sense at all. You're never allowed to cancel part of a sum or addition. It's one of the biggest mistakes students make when they're dealing with fractions. Now, what's great about this problem is the 2 to the 111 cancels. And then we'll just work what we have over here in parentheses. So 2 squared we know is 4 plus 1. Denominator 2 squared is still 4, but that's minus 1. Now, again, you can't cancel these 4s and these 1s. You have to go ahead and add 4 plus 1 is 5, divided by 4 minus 1 is 3, and that is your final answer. Hard to believe that this expression turns into 5/3, but it does. So I hope that helps you with the homework. If you have any questions whatsoever, please let me know, and I'll see you back for section 6-2.